Every device on Earth fights for an IP address. IPv4 ran out. IPv6 was supposed to fix it. But 20 years later, most of the internet still runs on IPv4. What if there's a protocol that makes both of them obsolete? IPv4 gave us 4.3 billion addresses. Sounds like a lot. But there are over 15 billion connected devices right now. We patched it with N18 network address translation, cramming thousands of devices behind one public IP. It works. But it breaks peer-to-peer connections, complicates security, and adds latency. IPv6 was built to solve this. 128-bit addresses. Enough for every grain of sand on Earth. But here's the problem. IPv4 and IPv6 don't talk to each other. Running both is expensive. And most ISPs just didn't bother upgrading. After 25 years, global IPv6 adoption is still under 40%. We need something different. Not a bigger address space. A smarter protocol. IPv8 isn't just a version number upgrade. It's a fundamental rethink of how devices find each other on the internet. Traditional IP protocols assign addresses to locations, your router, your server, your phone. IPv8 shifts to identity-based networking. Instead of asking where is this device, IPv8 asks who is this device. Every node gets a cryptographic identity. A unique key pair that works everywhere, your home Wi-Fi, a coffee shop, a satellite link. Your address doesn't change when you move networks. Think about what that means. No more DNS lookups failing because a server changed IPs. No more VPN tunnels breaking when you switch from Wi-Fi to cellular. No more NAT traversal hacks for peer-to-peer connections. The identity is the address. And it's secured by cryptography from the ground up, not bolted on like TLS was to HTTP. Here's how IPv8 works under the hood. It runs as an overlay on top of existing infrastructure. You don't need to replace routers or rebuild the internet backbone. IPv8 creates a peer-to-peer mesh that rides on whatever transport is available, UDP over IPv4, IPv6, even Bluetooth or local Wi-Fi direct. Each node maintains a routing table of cryptographic identities, not IP addresses. When you want to reach another node, you query the network with their public key. The overlay finds them regardless of where they physically are. It uses a technique called puncturing to establish direct connections even through NAT firewalls. Two devices behind different NATs can connect directly, no relay server needed. This is massive for decentralized applications. Chat apps, file sharing, blockchain nodes, IoT meshes all work without central servers controlling the connections. IPv8 doesn't just move packets. It builds trust. Every node can issue and verify attestations, cryptographic proofs about identity attributes. Imagine proving you're over 18 without revealing your name or birthday. Or proving you're a licensed doctor without exposing your license number. These zero-knowledge attestations travel with your identity. No central authority needed. No database to hack. This is where IPv8 gets revolutionary. The network layer itself becomes a trust layer. Today we rely on certificate authorities, OAuth providers, and government databases to verify identity. IPv8 replaces all of that with math. Peer-to-peer attestation chains that are unforgeable and privacy-preserving. Let's compare them directly. IPv4, 32-bit addresses, no built-in security, NAT-dependent, location-based routing. IPv6, 128-bit addresses, IPsec optional, no NAT needed but incompatible with IPv4 infrastructure. IPv8, identity-based addressing, built-in cryptographic trust, and AT traversal by design, runs on top of both IPv4 and IPv6. The key difference? IPv4 and IPv6 are about moving packets between locations. IPv8 is about connecting identities regardless of location. It doesn't replace the lower layers. It transcends them. This isn't theoretical. IPv8 is already running in production systems. Tribler, a decentralized torrent client built at TU Delft, uses IPv8 for anonymous peer discovery and trust management. No trackers, no central servers. The TrustChain system built on IPv8 creates a tamper-proof record of every transaction between peers. Think blockchain but without the energy waste of proof of work. It's being tested for decentralized identity verification in the European Union, peer-to-peer energy trading in smart grids, and secure communication for IoT devices that can't rely on cloud servers. Every application that currently depends on a central server to connect users is a candidate for IPv8 migration. IPv8 isn't perfect. Overlay networks add latency, every packet needs an extra lookup step before routing. Scalability isn't proven at internet scale. Finding a node among billions using only a public key is computationally expensive. There's also the adoption problem. IPv6 has been available for 25 years and still isn't universal. Convincing developers and ISPs to adopt yet another protocol layer is a massive challenge. And governments may resist identity systems they can't control or surveil. But the underlying research at TU Delft continues. The codebase is open source. And the need for decentralized, identity-first networking grows every year. Picture the internet in 10 years. Your phone connects to any network instantly, no reconfiguration. Your smart home devices talk directly to each other without a cloud server. You prove your identity online without giving away personal data. Payments happen peer-to-peer with cryptographic trust, not corporate middlemen. This is what identity-first networking enables. Whether it's called IPv8 or something else, this paradigm shift from location-based to identity-based networking is inevitable. The question isn't if. It's when. IPv8 might be the protocol that finally breaks us free from the limitations of location-based networking. But only if the tech community pushes for it. What do you think? Can identity-based networking actually replace IP addresses as we know them? Drop your take in the comments. Subscribe for more deep dives into the tech that's reshaping the internet.